Good day, I am Bea Bianca Rabaya, and as part of the fluid mechanics and hydraulics topic, I will discuss pipes connected in parallel. But before we'll dive into this topic, we need to know these three basic formulas for us to be able to calculate the discharge and head losses of pipes that are connected in parallel. For the first formula of the major head loss, we have the Darcy-Weisbach formula or the pipe friction equation. Now this equation is used to compute the primary pressure loss or head loss in a pipe, duct, or tube as a function of the pipe's length and diameter, the fluid's density and mean velocity, and the Darcy friction factor, which is an empirical value. So for the formula of Darcy-Weisbach, we have this. The major head loss for Darcy-Weisbach formula is equals to 0.0826 FL squared over D raised to 5. Now please take note that this is an SI unit. Of course, we have HF that denotes as the major head loss for the Darcy-Weisbach formula. We have F as the friction factor, L as the length of the pipe, Q as the flow rate of the liquid in the pipe, and D as the diameter of the pipe. We also have a constant of 0.0826. Next, we have the Manning formula. The Manning formula is one of the best known open channel formulas and is commonly used in pipes. Now, its mathematical representation is this. We have HF is equals to 10.29 n squared L Q squared over D raised to 16 over 3. And again, this is an SI unit. Of course, we have HF that denotes as the major head loss for the Manning formula. We have N as the roughness coefficient. We also have the L or the length of the pipe, Q as the discharge of the fluid in the pipe, and the D as the diameter of the pipe. We also have the constant of 10.29. Third is the Hazen-Williams formula. It is used in waterworks industry. This formula is applicable only to the flow of water in pipes larger than 50 millimeters or 2 inches, and velocities less than 3 minutes per second. This formula was designed for flow in both pipes and open channels, but is more commonly used in pipes. For its mathematical equation, we can come up with this. The major head loss using Hazen-Williams formula is equals to 10.67 L Q raised to 1.85 over C raised to 1.85 times D raised to 4.87. And again, this is an SI unit. And of course, we have HF that denotes as the major head loss in Hazen-Williams formula, 10.67 as the constant, L as the length of the pipe, Q as the discharge of the fluid in the pipe, C as the Hazen-Williams coefficient, and lastly D as the diameter of the pipe. Again, those are the three formulas that we need to remember in order to calculate the discharge and head losses in pipes connected in parallel. Now let's move on to our main topic, which is the pipes connected in parallel. Now, how can we say that pipes are connected in parallel? Now, one characteristic is that if the main pipe divides into two or more branches and again join together downstream to form a single pipe, then the branch pipes are said to be connected in parallel or is called compound pipes. To understand further what this means, I have here an illustration of what parallel pipes may look like. Now, this is an example of a parallel pipe or parallel system. Of course, we have Q in, or the discharge that goes inside the pipe, and Q out, which is the discharge that goes outside of the pipe. We also have Q1, Q2, and Q3, which just means or generally means the discharge in pipes 1, 2, and 3. As the fluid goes into the pipe, it will then be divided into three different discharges with accordance to the pipe properties. After the fluid or liquid passes through these three pipes, it will then come out with the same discharge as it went in. Now, with accordance to that fact, we can say that Q in is equals to Q out. We can also come up with an equation in which the total discharge is equals to the discharge at pipe 1 plus discharge at pipe 2 plus discharge at pipe 3. Or simply, the total discharge is equals to the sum of the discharge in all of the pipes. Now for head loss, our head loss are just equal in all pipes. So we can say that the head loss at pipe 1 is equal to the head loss at pipe 2 and also equal to the head loss at pipe 3. Since we're able to understand the concept of parallel pipes, let's dive into our problem number 1. Pipelines B, C, and D are connected with parallel to each other with pipeline B having a diameter of 450 millimeters and 600 meters long. Pipeline C is 400 millimeters diameter and 800 meters long. And pipeline D is 500 millimeters diameter and 700 meters long. The three pipes carries a combined discharge of 0.86 cubic meters per second. Assuming F is equals to 0.03 for all pipes, find the discharge of each pipes. In solving a problem, of course, we need to find the given. First, we have the discharge, which is 0.86 cubic meters per second, and the friction factor, which is 0.02. Now, going back to our concept, the head losses in parallel pipes are just equal. So, for our solution, we can say that the head loss at pipe 1 is just equal to the head loss at pipe 2. Since one over given is a friction factor, we can use the Darcy-Weisbach formula. Which is HF is equals to 0.0826 FL squared over D raised to 5. Now we can use the Darcy-Weisbach formula to calculate the discharge at all pipes. To substitute, we have the constant 0.0826 multiplied by 0.02, which is the friction factor. Next is the length, which is 600 meters, multiplied by the discharge at B raised to 2 over 0.05 raised to 5, which is the diameter. And then we have again 0.0826 times 0.02 multiplied by the length, which is 800 meters, multiplied by discharge at C raised to 2 over 0.4 raised to 5, which is the diameter of the pipe at C. For this equation, we need to find the discharge at C in terms of discharge at B. So we can cancel out the constants, which are the 0.0826 and the friction factor. So, 600 over 0.45 raised to 5 is equals to 32,515.3686. And then, 800 over 0.4 raised to 5 is equals to 78,125. Now, we have this equation which is 32,515.37 times QB raised to 2 is equals to 78,125 QC raised to 2. Now, we need to find the QC in terms of QB. So, let's divide both sides by 78,125, in which we can come up with 32,515.37 QB raised to 2 over 78,125 is equals to QC. Now, to cancel out the square at QC and QB, we just need to square root both sides. So now we have the square root of 32,515.37 times QB over 78,125. Therefore, our QZ is equals to 0.645 times QB. So, this will serve as our first equation. Now, to find our second equation, we just need to do the same things and the same concept. So, which is HFB is equals to HFD. Or, the head loss at B is just equals to the head loss at D. We'll also use the same formula, which is the Darcy way back. Since we already have a value for our QB, we can just write it down. Now to find the value for our head loss at D, we just simply need to divide the length over the diameter of the pipe, since 0.0826 and the friction factor will be cancelled. So we'll have 700 over 0.05 raised to 5. Again, we'll just simply divide the length over the diameter, which is 700 over 0.5 raised to 5. So we can come up with an answer of 22,400 QD raised to 2. Again, we need to find the value of QD in terms of QB. So we'll just use the same process as we did at equation 1. So, the square root of 32,515.37 over 22,400 times QD. By that, we can find the value of QD, which is QD is equals to 1.2048 QB. So that will be our equation number 2. Since we now have our two equations, we can now proceed to using our general formula, which is the total discharge is equals to Q1 plus Q2 plus Q3. Or in terms in our problem here, we can say that QT is equals to QB plus QC plus QD. Now, we just need to substitute the values of our equation 1 and 2, in which we have a total discharge of 0.86 cubic meters per second equals QB plus 0.645 times QB plus 1.2048 times QB. Again, we just simply substituted all the equations in our general formula. In this way, we can now calculate for our discharge at pipe B. So, for the discharge at pipe B, we have 0.3018 cubic meters per second. Now, since we already have a value for our discharge at B, we can now find the value of the discharge at pipe C and D. To find the value of our discharge at pipe C, we just simply need to use our equation 1, which is 0.645 times QB. Now, we already have a value for our QB, so we just simply need to substitute it. It will now become QZ is equals to 0.645 times 0.3018, in which our discharge at C is equals to 0.1947 cubic meters per second. Now, to find the value of the discharge at pipe D, again, we just simply need to use our equation number 2, which is 1.2048 times QB. Now, it will become QD is equals to 1.2048 times 0.3018, in which we came up with an answer of 0.37 cubic meters per second. This is how we will calculate the discharge or even the head losses of the parallel pipe using the Darcy-Weisbach formula. Now let's proceed to the second problem. If the discharge of the inlet and outlet is 0.05 cubic meters per second and the roughness coefficient is 0.013, find the discharge of each pipes. Of course, first things first, we need to lay out the given. Of course, we have the total discharge, which is 0.05 cubic meters per second, and the roughness coefficient, which is 0.013. Since one of our given is a roughness coefficient, we will use the Manning formula, which is the head loss is equals to 10.29 n squared L Q squared over D raised to 16 over 3. To solve this problem, we'll just need to use the same concept, in which the head loss at pipe 1 is equals to the head loss at pipe 2. Now, we can substitute everything using the Manning formula. So we have 10.29 times 0.013 raised to 2 times 400 times Q sub 1 raised to 2 over 0.3 raised to 16 over 3. Similarly, we will use the same formula. So we have 10.29 times 0.013 raised to 2 times 450 times Q sub 2 raised to 2 over 0.25 raised to 16 over 3. Now, we can cancel out 10.29, which are the constant, and also our roughness coefficient, which is 0.013 raised to 2. And now, all we have to do is to divide the length over the diameter. So we have 400 over 0.3 raised to 16 over 3, in which we can came up with an answer of 245,893.2646 Q sub 1 raised to 2. We'll use the same process at Q sub 2, in which 450 over 0.25 raised to 16 over 3, which we came up with an answer of 731,474.4047 Q sub 2 raised to 2. We need to find the value of Q sub 2, so we will divide both sides by 731,474,4047, in which we can came up with an equation of Q sub 2 raised to 2 is equals to 0.2646 q sub 1 raised to 2 over 731,474.4047. To cancel the square, we just need to square root both sides. So, we'll have an equation of q sub 2 is equals to the square root of 245,893.2646 times q sub 1 over 731,474.4047. In which we came up with an equation of q sub 2 is equals to 0.57979 q sub 1. And that is our first equation. To find our second equation, it is simply head loss at pipe 1 is equals to head loss at pipe 3. Since we already have a value for our HF1, I just simply need to write it out. Now, for our head loss at pipe 3, again, cancel 10.29 and n raised to 2. So we just simply need to divide our length over our diameter, in which it is 300 over 0.27 raised to 16 over 3. In which we came up with an answer of 323,480.3065 q sub 3 raised to 2. So the same process as we did in our equation 1, in which we came up with an equation of q sub 3 is equals to square root of 245,893.2646 over 323,480.7065 q sub 3. So, we came up with an equation of q sub 3 is equals to 0.87187 q sub 1. And that will be our second equation. Since we're able to formulate two equations, we can now proceed to use our general formula, which is the total discharge is equals to q sub 1 plus q sub 2 plus q sub 3. Again, we can just simply substitute everything. For our total discharge, we have 0.05 cubic meters per second equals q sub 1 plus 0.5798 q sub 1 plus 0.8719 q sub 1. Simply input everything in your calculator so that we'll be able to find our q sub 1 or our discharge at pipe 1. So for our discharge at pipe 1, we have 0.020 cubic meters per second. So since we already have a value for our q sub 1, we can now find our q sub 2 and q sub 3 by just using the equations 1 and 2. So the value of discharge at pipe 2 is equals to 0.011 cubic meters per second. Again, to find the discharge at pipe 3, we just need to substitute our value for Q sub 1, in which Q sub 3 is equals to 0.8719 times 0.020. So our discharge at pipe 3 is equals to 0.02 cubic meters per second. Again, in this specific problem, we use the Manning formula for us to be able to find the discharge in all pipes. Now, for our last problem, we have a parallel connected pipe has a combined discharge of 0.007 cubic meters per second and Hazen-Williams coefficient of 130. Find the discharge of each pipes. Of course, in solving a problem, you first need to find the given, in which we have a discharge of 0.007 cubic meters per second and a Hazen-Williams coefficient of 130. Since we're given a Hazen-Williams coefficient, of course we need to use the Hazen-Williams formula, which is the head loss is equals to 10.67 L Q raised to 1.85 over C raised to 1.85 multiplied by the diameter raised to 4.87. To solve this problem, we still need to use the same concept, in which the head loss at pipe 1 is equals to the head loss at pipe 2. And we will use the Hazen-Williams formula, in which 10.67 times 300 times Q sub 1 raised to 1.85 over 130 raised to 1.85 times 0.2 raised to 4.87 equals 10.67 times 266 times Q sub 2 raised to 1.85 over 130 raised to 1.85 multiplied by 0.18 raised to 4.87. Now take note, the units of these measurements are in meters. Now we can cancel out the constant, which is 10.67, and the Hazen-Williams coefficients in both sides. We can simply divide the length over the diameter, in which we have 300 meters over 0.2 meters raised to 4.87. And we have a value of 760,510.4323 Q sub 1 raised to 1.85. We also have 266 over 0.18 raised to 4.87. And we have a value of 1,126,430.852 Q sub 2 raised to 1.85. Since we're looking for the value of Q sub 2, we just need to divide both sides by 1,126,430.852. Now we have an equation of Q sub 2 raised to 1.85 is equals to 760,510.4323 Q sub 1 raised to 1.85 over 1,126,430.852. 126,430.852. To cancel out 1.85, we just need to multiply both sides with the exponent of 1 over 1.85. So now we have an equation of q sub 2 is equals to 760,510.4223 over 1,126,430.852 raised to 1 over 1.85 times q sub 1. In which we're able to come up with an equation of q sub 2 is equals to 0.8087 q sub 1. So, this will serve as our first equation. To find our second equation, again, we'll just use the same process as we find our equation number 1. So, we have our head loss at pipe 1 is equals to our head loss at pipe 3. Since we already have a value for our head loss at pipe 1, so we just need to write it out. To solve for our head loss at pipe 3, we just need to cancel 10.67 and the Hazen-Williams coefficient. Now, we just simply need to divide the length over the diameter, in which it is 510 meters over 0.25 raised to 4.87 times q sub 3 raised to 1.85. We're able to come up with a value of 436,116.315 q sub 3 raised to 1.85. Again, multiply both sides by 1 over 1.85 to cancel out 1.85. So we'll arrive with an equation of q sub 3 is equals to 760,810.4323 over 436,116.315 raised to 1 over 1.85 multiplied by q sub 1. And so, we're able to get the equation q sub 3 is equals to 1.3506 q sub 1. And that is our second equation. Since we already have our two equations, we can now use the general formula, which is the total discharge is equals to q sub 1 plus q sub 2 plus q sub 3. Now, substitute everything. We have a total discharge of 0.007 cubic meters per second equals q sub 1 plus 0.8087 times q sub 1 plus 1.3509 times q sub 1. In this way, we can be able to solve or identify our discharge at pipe 1. So, our discharge at pipe 1 is equals to 0.0021 cubic meters per second. And now, we already have a value of our Q sub 1, so we can calculate our values for Q sub 2 and Q sub 3. Again, simply substitute our value for Q sub 1 for the two equations. For our Q sub 2, we have 0.8087 times Q sub 1, which is 0.0021 cubic meters per second. So, our Q sub 2 is equals to 0.0017 cubic meters per second. We will use the same process to find our discharge at pipe T. So we have discharge at pipe T is equals to 1.3509 times 0.0021, which is the value of our Q1. So our discharge at pipe T is equals to 0.0028 cubic meters per second. Now this is how to calculate the discharge using the Hazen-Williams formula. So that's it for our pipes connected in parallel. Thank you for watching and listening. God bless you.